Hey everyone, I'm Nick, and welcome to another episode of Advanced Topics. So in this episode of the series, we're going to be talking about thread affinity. So when we're writing a multi-threaded application, there's a number of things we have to think about in terms of performance. So one of the things is how we're partitioning our data. So we want to make sure we're avoiding things like false sharing. Another thing we want to look out for is how we're distributing work between threads. So we don't want one thread to be doing all the work while other threads are doing nothing. Now, another thing we have to think about is how our threads are being placed to different cores or to different NUMA nodes, because this can have a significant impact on performance. We may have some inter-thread data locality, and the operating system might not be aware of this. So your operating system is what's actually scheduling these threads. So in this example, we're going to be taking a look at two different benchmarks, one of them where we rely completely on the operating system to make these scheduling decisions, and another one where we give some hints to the operating system on how it could better schedule our threads. Now, all these threads are doing is calling this work function. So it's just trying to do 100,000 atomic increments on some atomic integer. Now, in this case, threads 0 and 1 will be working on the same atomic integer that I've put in this aligned atomic struct. And this is just to make sure that these aligned atomics don't wind up on the same cache line, trying to avoid some false sharing here. So T0 and T1 will be working on this aligned atomic A, and T2 and T3 will be working on this aligned atomic B. So what's the problem if we just let the operating system schedule these threads as it sees fit? So the problem comes with the fact that what happens when we're doing these atomic writes, or what happens when we're doing memory writes in general. So if we want to do a write to memory location, a thread first has to get exclusive access to that cache line. And it does so by changing it to being in the modified state and invalidating all the other copies that are out there inside of the system, in any of the other caches. So if T0 and T1 are far apart from each other, that means you're going to be just pulling that cache line back and forth as they're trying to do those atomic increments to this aligned atomic A. And likewise, threads 2 and 3 will be having the same competition over a different cache line, this time for the cache line that this aligned atomic B is sitting on. So in many cases when we're writing multi-threaded applications, we can't avoid having, or we can't have a multi-threaded application that has no sharing. There'll be parts of our application that we can't get around the sharing, but it's important that we understand how we can mitigate these problems. So we can help mitigate these problems through better thread scheduling and placing threads that have this sharing close together. So the first thing we'll do is we'll just see how well can the operating system do so without any help. So we'll go ahead and compile this benchmark, and what we're going to be taking a look at, or mainly focusing on here, is our L1 data cache miss rate. So that'll be a good indication of whether or not these cache lines are being constantly invalidated and pulled back and forth. So we'll just do perfstat-d, and we'll run our OS scheduling benchmark. And you can see we get a pretty high miss rate here. So over 50%, 51.65%. And it took about 3.63 milliseconds to run. And we can run this multiple times. And you can see that we can get very different results. So now it took 4.6 milliseconds with 35% miss rate. And the key thing that's kind of going on here is that, the operating system does non-deterministic scheduling, So the scheduling will depend on the current load of the CPU. So when you run this multiple times, we may get slightly different scheduling results, which will lead to slightly different L1 data cache miss rates. But you can see that no matter what, that miss rate still seems to be fairly high because these threads are likely getting placed on different cores. Now, we can zoom in a little bit more and understand this direct sharing that's going on by using perf C2C. So perf C2C isn't just a great way that we can debug things like false sharing. It's just an overall good tool that we can use to debug or understand sharing in our applications and contingent for cache lines. So we'll use perf C2C record followed by perf C2C report. And you can see that we get the shared data cache line table. So this is a table of all of our heavily contingent cache lines. And you can see that there's two here. So one of these cache lines will correspond to our aligned atomic A. The other one will correspond to our aligned atomic B. So both of those are being contended for by two threads. Okay. So if we go ahead and take a look at one of these cache lines, so we'll take a look at the one at index 0. So I'll press D in order to open up this next menu where we're zooming in on this particular address, this cache line. you can see that, it's a roughly 60-30 split for these hit M's. And so a hit M, just as a reminder, is when we looked over the bus for a cache line and we found that some other core had it in its cache in a modified state, basically meaning that we're looking out many times over the bus and we're finding someone else writing to our cache line. So a common indicator of something like false sharing or direct sharing. And you see in this case that both of these threads are accessing the exact same offset in the cache line. So they're really accessing the exact same data. And you can see over here exactly which threads these are. So these will be lambdas 1 and 2. As you can see right here, so these will just correspond to threads 0 and 1 respectively. And then you see the CPU count column. So this is an interesting column to look at when we're thinking about scheduling. So what does CPU count correspond to? Well, CPU count corresponds to not which core that this thread wound up on, but the number of cores where samples came from during execution. So, when your operating system schedules a thread to a core, it doesn't just wait for the thread to complete, right? It may move the thread to a different core if it thinks that it's advantageous to do so. And we can see if we go ahead and look at the other cache line, we see something kind of similar. So this time, these threads moved around, to 8 and 7 cores respectively, right? And again, this is just accessing right from the exact same cache line, the exact same spot. And these will be threads 2 and 3 respectively, so corresponding to lambdas 3 and 4. Okay, so we can see that if we just rely on the operating system, it can make some suboptimal decisions, and now we kind of understand why, right? So these threads are just kind of floating around. The operating system doesn't know, where the data locality is, so we can end up having a ton of contention for these cache lines. So let's see how we can kind of help the operating system out by setting the affinity for some threads. So how we set the affinity will depend on your actual native thread implementation. So it's not something that you set just from your C++11 threads. You've got to use whatever library is being used underneath by your C++11 threads. So in my system, it's going to be pthreads. So I'm going to have to use some stuff from pthread.h. If you're on Windows, you'll have to use whatever functions are specified for setting the affinity for your Windows threads. So let's see how we can do this for pthreads. So not only will I create my online atomics here, but I'll create the CPU set. So this is coming from pthread.h. So the CPU set is just going to be the set of valid cores where I want to schedule threads. So I'll create 2 of them. I'll create a set of cores for threads 0 and 1, and a set of cores for threads 2 and 3. Because 0 and 1 have some interthread locality, and threads 2 and 3 have some interthread locality. So then I'll go ahead and initialize them by just zeroing them out. And then I'll go ahead and set 1 core for each of these sets. So CPU set 1, I'll just set core 0 to be in the CPU set. And then for CPU set 2, I'll just set core 1 in this set. So basically, I'm going to use this pthread set affinity in P, and I'm going to pass it CPU set 1, basically saying I want this thread to go to whatever the cores are specified in CPU set 1. And you can find the full specification here, which I'll link below, and this on this man page for pthread set affinity in P. So one thing to note here is that we can't just directly pass our C++11 thread to something like pthread set affinity in P. You see, it doesn't take a C++11 thread here, it takes a pthread T, or it takes a handle to a pthread. But we can get the native handle to a C++11 thread fairly easily, so there's a method to do so. So we can go ahead and just call this native handle method, and it will return, right, in this case, because we're using pthreads, the handle to our pthread. So I can create my C++11 thread as normal, so I'll create a std thread T0 and a std thread T1 here, and then I'll call pthread set affinity in P for each of these threads using T0.nativeHandle, the size of the CPU set T, and then I'll pass a pointer to the set that I want to use. So I want to use CPU set 1 for threads 0 and 1, and then I want to use CPU set 2 for threads 2 and 3 respectively. And then I'm just wrapping these in an assert. That way, if something goes wrong when I'm setting the affinity, I'll just end up crashing the program. Okay, so let's see how this benchmark compares to when we just let the operating system make all the decisions for us. So now I'll use perfstat-d again, except this time I'll be running the thread affinity benchmark, right? So let's see what we get. So now it looks like we have a much lower L1D cache miss rate, so a very high hit rate. So only about 2.81% of our L1D cache accesses ended up being misses, right? So that's pretty good. And also, our time that it took was only about 0.9 milliseconds, so also pretty good. So just as a reminder, for our OS scheduling benchmark, right, we had, a 34% L1D cache miss rate in this case, and it took 5.12 milliseconds. So that's roughly five times slower than when we set the Affinity, right, where we told the operating system, hey, I want you to schedule these threads, right, only to these cores, right, because I know what I'm doing as the programmer. I know where my interthread data locality is. If I place threads that are accessing the same data on the same core and they're doing writes, they're not going to have to invalidate each other. And you can see if we run the OS scheduling one multiple times, we still do get different results. So different data cache miss rates and different timings even. So even in like the best case, we're getting down to say 3.42 milliseconds, which is still over 3 times slower than when we were doing thread affinity. And you can see that the thread affinity benchmark is fairly consistent. It's always around this 0.943 milliseconds. And that's because there's not a lot going on here. The operating system isn't bouncing these threads around to different cores. They're just kind of sticking to the cores that we set the affinity to. So that's going to go ahead and do it for this example. It's a brief introduction to kind of pinning threads to particular cores by setting the affinity of these threads. Like I said, exactly how you do this will depend on whatever your thread library is. So if you're on Windows, it'll be different. If you're on Windows, if you're on something like a Linux system and you're using pthreads, it'll likely be very similar to this. But that's going to go ahead and do it for this video. I'll put a link to this native thread handle and this pthread set affinity in P below the video. And you can check out any of these benchmarks on my GitHub page at github.com/coffeebeforearch. So feel free to send me any questions you may have. And as always, I'm Nick, and I hope you have a nice day.